So, um, a lot of nice information and a lot of visions and really hard core facts that this is happening right now. Then a lot of questions that we have continuously when we meet our clients is, okay, so what hardware is required? Can I run this on a real-time OS? Do I have to run Linux? Can I run this on a small MCU, or do I have to use a really super duper NVIDIA-based server? So what I will go through today is a few examples of various hardwares and what you can expect of these hardware, because I think it's essential for you to understand the limitations of the hardware that you are sitting on right now, or if you, in case you need to develop something new, is it worthwhile? And of course it is. So, first of all, where to use AI, and everywhere. We saw this picture in Janne's presentation. More or less all verticals today can utilize AI on edge. And specifically this on edge, you see the powerful stuff that the rest of my presentation is about, that you have been able to utilize Google features or cloud-based features for a long time. We helped Spotify to develop this car thing, which was a voice control or multimodal control to the smartphone that run the Spotify application. And you said, hey, Spotify, play albums by Madonna or a specific song by Madonna, whatever. And the trigger wake word was in the device, and the rest of the voice were sent up to Google ASR, where it was translated to a text and then sent to an NLU to understand what the intent was, but whatever I said. And then the result was sent back to the device. Even though this latency was not like massive, it's still a latency and it consumes power. And I think that what happened right now is that now things are happening on the edge and you don't have to bother about going into features in the back end. You don't then have to be connected through cellular connectivity. You don't have to bother whether you have a Wi-Fi connection or not. This is maybe borderline AI or machine learning, but you can argue for that it is because you learn it. So this is, it happens to be STM. There are other sensor manufacturers as well. This is a small IMU, accelerometer and gyro, or accelerometer compass, or accelerometer, gyro and compass, what have you. This now comes with a small, or some of these devices come with a small module that makes them run a small, it's finite state machine, so it's not AI, it's not a neural network, but it can create various decision trees. So based on training, it can learn to detect motion like running, walking, shaking, dancing, etc. So this can be used for very simple motion-related activation detection, kind of. You can always use these kind of devices for anomality detection, for predictive maintenance. Is something starting to vibrate or move in an accurate way? But this is taking it to a certain level. But this is not like massive AI, right? We need more. This is something that we have heard about today at Nordic Semiconductor, where you have this Newton AI model running on it. So I don't dwell on it that much, but the thing is, this is Nordic. This could also represent a small MCU. And what is a small MCU? Then, well, as a core of some sense, nowadays everything is running ARM cores. So this could be like a small M33 core running, as this example would be like 128 megahertz clock, but there are many MCUs running on way lower clocks than this. And they come with embedded memory of maybe 64 kilobyte or 128 kilobyte, or in Nordic's case, even up to 1 megabyte of RAM, which like enables larger models. But you can, from a capabilities perspective, you can have some kind of general ML that you can do what we learned. Daniel, are you still on? No. But so what we learned is that you can do a lot of health analysis related stuff. You can track illness, people, elderly people, you can make things, the living easier for them, and we can have anomaly detection for if they fall and if they behave differently compared to every other day, like patterns, motion patterns, behavior patterns, things like that can be easily done with a small MCU. But that's not cool enough, right? So we need more. Now, this is a brand new platform. I can't talk that much about it. It's presented, the AR1 Plus. They have XR chipset, they have AR version, but this is AR1 Plus. So Qualcomm are working heavily with their AI capabilities in their chipset, and this is a family of chipset intended for smart wearables, like smart glasses. Maybe you have seen the Meta Ray-Ban glasses that have a lot of nice features in them, and these are just evolving rapidly. So now imagine that you have a small NPU, neural network processing unit in it. So now you're starting to run neural networks. Now we're really AI. Now we have also memory that are some gigabytes. This is not sufficient to run the larger large language models, but you can run downscaled version of those small language models, or even a kind of limited version of large language models. Now this enables you to have your own AI assistant on edge. You can have your smart glasses to see what you see. So you have this. I didn't add the capabilities in computer vision because that's kind of unofficial information. I can't share that yet. But you can have VLM. VLM is a vision language model. It's a combination of vision and a large language model. This is where you can talk about what the camera see. So now you can use your glasses and you can look on this crowd and you can ask your agent, how many people are in this audience? And it will tell me that. Either verbally, like in a speaker, but it can also have like a small display or a projector inside my glasses, which is like typical for smart glasses. So now I can see in text, real time, there are 55 people here. How many are over 50? And I can have this chat going on. On the edge, there's no cloud connecting at all. And this is just, to me, it's overwhelming. This is super important because, going back one slide, imagine that you are a service engineer going out in the field, trying to repair some stuff, and say, hey, guy, this is what I see. Where should I start? And then the AI engine will say, well, it seems like there's a missing bolt up to the left. So this way, engineering in many different areas, service engineering, a lot of things can be managed in a super skilled way and executed faster, and you don't have to call back end service. And of course, you need to be able to trust this model, though. But they are getting better all the time, and along with training, of course, you train this model for your specific task. In this case, servicing a motor or servicing a lawnmower or whatever. Okay, and this was the first Linux-based. I didn't see that, but the small MCUs could run FreeRTOS or Sapphire OS, meaning that they can run on a small memory. As soon as you add Linux and you add gigabyte of RAM and gigabyte of non-volatile memory, then you add also all these capabilities. Now you run CPUs that are running probably on gigahertz clocks. So now we have a really powerful engine. This represents a generic application processor. This happens to be NXP's IMX95, a brand new application processor. Could be an application processor from Qualcomm, could be a TI or anyone. So now we're talking an NPU, a neural network accelerator that have 2 TOPS. And 2 TOPS is not, in this world, it's not much. So 2 TOPS, tera operation per second. This is how many processing steps that the AI engine can run. And this is one area where people are mistaking themselves. So if you compare 2 solutions, so this have 100 TOPS and they have 2 TOPS, then this must be like 50 times better, right? And that's not true, really. it's a very clear sign that this is better performing than that one. But if you, on the other hand, have a slow memory access, so the DRAM bus system is really slow, you'll have a lot of latency. And also, if you're running a lot of stuff on this platform, so that you're overloaded with all the other stuff. You have Linux running, you have applications running, you might have the computer vision running, and then also you would like to have this small language model running something. So then 2 TOPS is not that much. And the memory access speed is super important to get not only the inferencing time, the latency that we talked from whenever it sees a picture, for example, until I get the inference response back. That is essential for real-time applications, where if I drive a car and then I pass the road where I should turn right, and then 50 meters later I'll turn right, like crap. Okay, so now an application process can run computer vision, and what we see here is a good example. It happens to be that we are developing right now on this application processor, and the performance that you see is, I have to do this, sorry. So the performance here is like, if you have 2 video streams simultaneously running, in this case they need 3 actually, but we have 2 running, where one is VGA resolution and the other one is HD or HD ready. Then you have approximately 100 to 200 millisecond latency, and you get something like 10-15 frames per second in the lower resolution, and 5 to 10 frames per second for the HD. That's not really that much, right? And this is where a lot of application processors today are, and this is very new. Then we realized that, okay, so let's add a coprocessor to that. And this is, by the way, a full European scenario. There are today different industries that require all European supply chain. So this is a very powerful platform. Both of these companies are Dutch. So this is truly a full European supply chain solution. Accelera, fairly a new company. They have been around for a few years, still to be considered as a startup. They perform 214 TOPS. Again, that's not all, right? 2 TOPS is not all, but 218 TOPS indicates something that is better than 2. This connects to the application processor some interface, in this case a PCI Express interface. So that is one possible bottleneck. So you need to transfer video stream from the application processor that runs the cameras, and then data over to the coprocessor, and then it's processed there where the inferencing is at, and then you get inference response back to the host processor. So there are some latency here. Running here again. Remember what we had on the prior slide, we had like 5 to 10 frames per second, and we had a latency of several hundreds milliseconds. Now we're down to 30, 40 frames per second-ish, and the latency is in the range of 15 to 20 milliseconds, or 25 to something. Now we should remember that 30 frames per second, each frame is valid for 33 milliseconds. So the latency here is sufficient to get an inference response within 1 frame. Before the next frame, you have already gotten the response, what you see. Now we can run a visual language model. Again, you can discuss with the device about what I see, how many have glasses in the audience. We have also the possibility to run larger language model, but remember that the prior slide, we had a little limited memory, the RAM. So Linux requires memory, and a lot of application processors then require, or so that they support maybe up to 16 gigabyte of RAM. Some of them support more, but it's not uncommon to have an 8 to 16 gigabyte of RAM limitation. And that's not sufficient to run large language models. You can maybe run optimized large language models where they become a little less, you can't really discuss with that language model in the same depth and the detail and depth that you could with an unlimited large language model. But this one, now we're running okay, so it's running Linux, but there's nothing else on it. So most of the memory can actually be used for the large language models. And now we can run 8 billion parameter models on this. This is really good. This is really capable. And then we're getting to the end. NVIDIA Jetson Jetson. A lot of, or most developers are actually thinking NVIDIA when you think about AI and computer vision and all that. And they have really been skilled on that. They are using, remember they come from the GPU, right? So they are using a lot of GPU cores in their designs. In this case, this is the Orin Nano. They have, 1024 cores in their GPU. And then some additional one that they refer to this CUDA, tensor cores. And then they have some other stuff. But anyway, they are consuming quite much power. So when you compare this platform, you can set it to different power modes, like up to 25 watts, which is the maximum. And that's then you can peak a little bit higher than that, which is what you need to do the performance that I have stated on the right-hand side, which is very close to the same frame rate and the same resolution and the same latency as the one that we have here with a coprocessor. But this coprocessor and in this case the IMX95 consumes less than half the power of NVIDIA, and it costs way less than half of that solution. This is typically like a $150 at the low volume. Sorry, that is $150, while the NVIDIA Jetson Orin is several hundred of dollars, closer to 300-ish. So it's a good example of where things are moving, because this is where everyone starts. And actually, when we talk to Accelera, they have a lot of companies coming and saying, we started with a Jetson and now we want to move to something else. Can you help us? So their starting point is almost always some Jetson model from NVIDIA. And I was asked by Janne, okay, to bring examples, what can you do with this? And I think that the most visible example I think I can give is exactly what I mentioned. I am sitting as an engineer, service engineer somewhere. I don't have a clue what's wrong with the shit. And I ask it, can you see what's wrong? Is there something missing? And your agent will help you, and we can guide through steps. Okay, I need to replace this oil filter. What should I do? Well, okay, so take off this bolt first, and then you unscrew this counterclockwise, and then you remove the whatever. So this kind of discussion is possible. And you can do this with all these Linux-based solutions, I would say. It's hard to say that you can do this with your free RTOS or RTOS-based systems. So this is just to give you, I will leave you to that. You don't have to read it. This is just to give you a spectrum of everything from a few dollars for the tiny IMU up to $300+ for the NVIDIA Jetson Orin NX. And where you are on that scale totally depends on what you are asking for. What do you want to do? Multiple video streams? Well, okay, so then it's more expensive. Do you want to do computer vision? For sure, a Linux system, not an MCU-based system. Do you want to have vision language model where you can ask and discuss about the picture? Then the higher scale, the more expensive solutions. And you can have 30 frames per second or even 60 frames per second in real time, having inference response within the same frame. Like, to me, that's mind-blowing. Does it sound reasonable? And there are more examples. I mean, these are just to set kind of a kind of chart. Any questions? That means that I was totally perfect and totally covered.
I think it also ties back a bit to I mean, the way we typically also approach our clients is that we always want to start with what we call a definition phase. with the likes of Håkan from our system team to do the system architecture to not end up with an NVIDIA if we didn't need it.
Mm.
So, I mean, start in the right part. I know everybody's hungry, so while I prepare the food, Håkan and our previous speakers will do a small Q&A, and when that's done, welcome to enjoy the food.
I go under the name of Lil Ernst at our company. So this is my Ernst way of questionnaires. Karin, we have a question for you. So in your presentation, you show how smartphone function dissolve into glasses and wearables and sensors and all these other infrastructures stuff. Which of these interfaces do you expect to be the kind of mainstream device first? If you look for what will be the biggest in volume, sales volume.
Kan du ta frågan igen?
Yeah.
Det var lite
So
trött.
when you have like all these wearables on you that replace your smartphone. Today, your smartphone is the centric piece.
I think it's going to be the audio. It has already started actually. I mean, we've gone from in-ear to open-ear earbuds, for example, and it requires AI support in form of the audio will have to come from different directions, so spatial audio, for example. And the next that will come is the glasses. And they will initially be connected to the smartphones. For them to be connected to the watches, so we can get rid of the smartphones, we will need better messaging capabilities in the glasses. And that will in turn require better text-to-speech and speech-to-text convergence. So that's how I see it. So audio first.
Audio first.
And then glasses. And then to get rid of the smartphone connection and connect the glasses directly to the watches.
Right.
We need to improve the messaging.
Thank you. Thomas, your work with edge operations is uncontrolled outdoor environment where conditions are kind of harsh. Where was the moment where you realized that cloud AI cannot resolve this, but you needed to have on edge processing?
I think the precise moment was actually when using one of our previous mobile providers, I was actually testing our alpha unit of this at home, and I actually have good connection, but thanks to bad cellular provider, I realized that even in the backyard where I live, we can't rely on this. And that was like my own intuition, but I think several of us at the company had the same similar intuition that we needed to be able to operate off the grid.
And was the business part of it, like the cost for subscriptions, was that part of that decision as well?
No, it's just reliability. And we're working with partners now and with customers like Trafikverket up north, for example. I think when we live in Stockholm and in big cities, we just take it for granted that you're always connected. And when you, like in my case, I was surprised because it wasn't that far out, but our customers, farmers, roads, connectivity just doesn't exist there yet. And the motivation to actually push connectivity there too is probably not that high because there's not much value to gain from it. So I think we have to be realistic and that we're always going to operate under low connectivity.
Karin, you presented the idea that AI is a glue in connected in human physical and digital worlds. In practical terms, what is the first everyday experience where people will feel the shift without really understanding that it's AI doing it?
We don't need 6G to actually experience AI. I mean, we already today have a lot of image editing features, image manipulation. You can take a picture, you can remove the background, you can turn the image into a video, for example. So that's already existing today. Next step is again this better speech to text, text to speech, and also steering our glasses with, you know, gestures, motions, hands, our bodies, heads, etc. That
So-
will also require AI, of course.
If you look on the features in the 6G network, will there be any AI features in that network? I'm thinking, my initial thought, well, okay, so this is going back to the old switchboard. Hey, please connect me to Karin. We already do that with your phone, right? Please call Karin. And so I already use verbal control, but that's in my device, not in the network. Do you think that these are features that will go into the network directly instead?
Oh, that's a good question.
That is the old switchboard.
Yeah, that's the old switchboard. I mean, I think it will be a revival of the voice, actually.
Yeah.
Because it's so much simpler than having to text. And maybe as you know, a field engineer could maybe speak to the different network nodes when doing repair, instead of having to read a manual and go through different steps, you know, in doing when trying to identify what's wrong, you know. You can instead speak to the node.
Interesting. Well, take the last thing, because I think that we're the last question, and this is for the full panel, so I also got to talk here. So Thomas stated latency kills understanding. Karin presented how 6G collapses latency and distributes the power and the compute across devices and edge, etc. If latency becomes near zero, what fundamental changes in how we architect intelligent systems would you perceive? If we get close to zero latency, would that change the way we think in architecturing stuff?
I think in order to reach zero latency, I mean, that's a consequence of a change in the network architecture. Right?
Yeah.
So that's one thing. The other thing I'm thinking about is, for as long time as it will require massive amount of energy to do AI processing, AI inferencing, it will probably be so that the vast majority of the AI inferencing will take place in centrally located data centers. And it's all because of cost efficiency. It's not because the network cannot handle the inferencing at the edge or inferencing in the devices. It's because of the limitations of the energy system.
That's a good point. Should that be?
Yeah, I mean that's a good point. I was thinking something similar where, I mean, latency is obviously a problem, right? And when we operate around it, but I think as intelligence gets pushed more and more to the edge, latency becomes less and less of an issue, to be honest. And I think less latency means less energy. Like if we don't have to spin up a network card, we'll save a lot of power, right? So I think, native intelligence will actually solve the latency problem in one way, in a kind of backwards way, because we don't have to push as many bits. Information is heavy to push around, but we already encode video, we encode a lot of different signals to make them efficient. And if we can actually handle most of that on the actual edge, we have to push even less signal back and forth, or more compressed signals at least, because machines are much better at interpreting themselves. Where whereas humans, like we rely on, well, like sound, right, to communicate.
Mm.
And yeah, system can communicate with much smaller
Good point.
bandwidth.
I will add the last comment to this question before dinner. When you have user interaction, latency is essential. Low latency is essential for having a flowing communication. And for many of the hardware solutions that I presented, they could be used for aiding different, like hearing aiding and visual aiding. So let's assume, for example, that you are totally deaf, and I have my smart glasses with a projector on it, so I can read text in my glass. So if my microphone hears what you're saying to me, and then I get the voice to text translation in real time, which is like happening on these ships. It's just that there is a latency right now of approximately 1.2 seconds for the first token. It's called time to first token. When you do things and then it processes and then the first token comes. This would be the first word in this case. So 1.2 seconds is really too long right now. When you come down to 40 milliseconds, this is where it gets really indistinguishable. Then you can have a totally fluid conversation. Now we can have people that are totally deaf communicating with anyone, as long as they remember how to talk, which was many of them becoming deaf when they're older. Then they still remember how to talk. So yeah, zero latency. Thank you.
Thank you all.
Thank you.